Okay, cool. I'm Steffen. This is joint work with Arya Klagesmund. We're both at Superluminal Labs. And today I want to talk about the design of the primary algorithmic market maker of the Gyroscope stablecoin. So Gyroscope is a stablecoin, and it's non-custodial, meaning that it's completely on-chain. It manages other assets, and I want to talk about the design of such mechanisms. And so the super high level of how stablecoin works that you should keep in mind is this. There's the coin, and it's stabilized in the following way. We have a mechanism which is called the primary algorithmic market maker, and it moderates access to a reserve of, to some pool of assets. And people can come to the reserve and mint and redeem units of the stablecoin against units of these assets. And this is what's going to stabilize the price. Now, what are these assets? This, of course, depends on what the stablecoin is. In a semi-rush share style design, like Terra, for example, or a pure Terra, these would be something like equity shares, something like that. In something like Basis, this would be like bonds. What's important to note here is that these assets are kind of endogenous. They are very tied to the value of the stablecoin itself. And in reserve-backed systems, like how we designed Gyroscope, it's a portfolio of some other assets. Now, of course, in normal times, where these assets are at least 100% of the outstanding supply, you can just mint and redeem at a value of 1, and the value of the stablecoin is perfectly stabilized. What we want to look at is what happens in a crisis where the system is less than 100% collateralized. And so we're going to spend some time on this. Kind of the motivation for this is that we believe that any stablecoin needs to have a plan what to do in such a crisis. And the main tool we're going to use are what we call a redemption curve. So the redemption curve is the price of redeeming a stablecoin as a function of the total redemption happening at any point in time. So the graph looks like this. What would be ideal is if we always get $1, but as I said, the system is under-collateralized, so we can't really have that. The higher the curvature of the redemption curve, the shorter the amount of time where the price is supported, and the quicker the coin will collapse. What's happening in many, let's say, pegged fiat currencies is that the central bank tries to support the price at $1 for as long as possible until it becomes politically unpopular, at which point the price is not supported at all anymore. And this is something that has enabled speculative attacks, for example, on the pound in the 90s, where we can see this very nice and very abrupt collapse that can give some speculative benefit to some traders like George Soros. We've also seen this picture. These are various stablecoins over the course of the first half of 2021. Maybe you see a similar pattern there, and maybe this is an additional motivation to look at what these curves look like. I want to talk about two case studies very quickly. One is the original design for Fei. The curve without direct incentives would look something like this, because this comes from a constant product market. But Fei introduced these direct incentives where traders are kind of quadratically punished for redeeming coins at times of high redemption, which means that the redemption curve actually looks like this, so very quickly collapsing, which may have been the contributing factor to this very unstable price at the launch of Fei. Another interesting case study is a semi-rush share mechanism, where you formally have redemption at $1 worth of assets, but the backing of the coin is this endogenous asset, this semi-rush share, which can lead to negative feedback spirals. And so what we should expect is, again, something like this, that we have redemption at $1 for a long time, until at some point confidence of the market breaks down and we very, very quickly go to zero, which is also something that was reflected, for example, during the collapse of the Iron stablecoin and its associated endogenous backing, the Titan token. So these were as you can see, these were very, very correlated in their collapse. The idea that we had was, let's start at the redemption curve, because usually what happens is that the designs are just there and then we infer the redemption curve from that. Let's choose a redemption curve that we think is reasonable, implement a primary algorithmic market maker from that. And so we have these three research questions. First, what desiderata should such a curve satisfy? So we're able to choose one. Can we then specify one such curve that we think is good? And then finally, can we also implement that on chain, of course? Right, so keep in mind that the model should be something like this. The primary algorithmic market makers regulates access to a reserve, and to make our life a little bit easier, let's assume that the reserve is an exogenous portfolio, so it's not correlated with the price of the actual coin, because otherwise we have all these problems, which might be like a separate question. So let's look at some desiderata. This is what we came up with. I want to go through them very quickly. Collateralization should be greater or equal to some lower bound, so the mechanism itself should not exhaust the reserve, if this is possible, of course. So if I apply an exogenous shock to your reserve that's large enough, of course it will be exhausted. But if that's not necessary, if we are able, we should be able to ensure some lower bound. The same should be true for the redemption price, so there should always be like some level of stabilization if this is at all possible. Normally, of course, we want $1. This seems to be pretty relevant, that the redemption curve is continuous and not too steep to deter speculative attacks, where someone could make a relatively small redemption amount to lead to a high decline in the price. This is not what we want. This is also something that's nice to have, that we don't want to create incentives to subdivide redemptions. For example, when our fees would be weird, there could be such an incentive. This just makes everything complicated for traders. We also have some desiderata that should hold like over longer frames of time across blocks. Don't want to go over them in detail. Of course, this one should always hold. You should be able to implement it, and this is also what I'm going to talk about. Let me now give you one such curve. And the first thing I want to define is how are we going to compute the redemption level. And what we settled on is that what should be on the x-axis is a time-discounted sum of redemptions at some time. So of course this doesn't matter if all your redemptions are happening like infinitely fast. Then this discount factor here doesn't matter. But you need to take time to account somehow, and this is how we do it. Now I want to give you one simplified design that satisfies almost all of the desiderata, which is this one. So there are like two parameters. I'm going to talk about them in a moment. We start at some collateralization ratio. So these R values are always collateralization ratios. They're between 0 and 1. And we have a lower bound on the collateralization ratio. If we start at a point that is below that lower bound, we just redeem at the collateralization ratio. So we basically say there's nothing we can do. We choose the best redemption rate that we can. So let's, without loss of generality, assume that it's like between our lower bound and 1. And then what we can do is that we say, well, there's a certain threshold of redemption. And up until that threshold, we support a price of $1. And this is to ensure that as long as the redemption pressure is not too large, we always support the peg of the stablecoin as well as possible. And as soon as we are at this point, we drop the redemption price to the collateralization ratio. And this we can keep infinitely. So for example, if the coin is 80% collateralized, we can redeem at 80 cents on the dollar. Now this thing we need to choose, and what we can do is we say let's maximize this point until we support the coin such that eventually the collateralization ratio will be above our lower bound. And of course it's that if you support the peg for longer, while you are doing this, you are making your collateralization ratio lower and lower, because you offer a redemption price that's too high in a certain sense compared to the collateralization. And so the longer we do this, the lower eventually the rate will be here. So there's a certain trade-off there. And I think I have the formula to do it. Right, so this would be the formula to get the maximal value so that this is above the threshold. Okay, and now we can go and check and see that this satisfies all of our desiderata, except for one, which is of course this annoying fact that this is like very discontinuous. And this is something we don't like. And so the solution we really propose is a piecewise linear function that looks like this. We have a point, we have a segment where we support the price at $1. Then we have some linear segment where we decrease the redemption price linearly. And then finally, at some point, we keep it constant again. And this point is when the collateralization ratio is equal to the redemption price, so that this function here is continuous. And now we have two parameters to choose. We have this slope here to choose, and we have this cutoff to choose. And the way we propose is that we say there's a certain trade-off. So the longer you support, the longer you support a price of $1, the steeper you have to make this so that it works out. And what we say is this slope is more important because it's important that the price decline does not become discontinuous. And so this is the new rule. We first minimize this slope alpha, and then up to a certain point. So this is a parameter. You can choose a threshold where you're saying, as soon as I've reached the threshold, it's like flat enough. You can set this to 0, in which case you get some kind of like extreme construction that still works out though. And then as a second priority, we maximize the point where we support at $1. And this we can still solve, and it looks like this. It's a little bit more complicated, but what you see, it's basically a bunch of case distinctions and then some calculations. Okay, let's now think about implementation. First question is, how do you do actual redemptions? Let's say we have this function. How do we do redemptions? Well, there's some redemption level that we observe. Let's say this one. And there's some amount that the trader wants to redeem. And we go from the observed redemption level here to the as much as they want to redeem, let's say here. And then we integrate over the redemption price. So the redemption amount will be the integral over this redemption price, which we can, of course, do analytically. We don't have to do it like numerically or anything, because these are very simple equations. But the problem is we don't necessarily know this curve. So assume we have defined this curve by this parameter RA. But at any point in time, where we will be is a state on chain where we have a certain collateralization and we are at a certain redemption amount, and then we need to deal with this. So what we have to do is we need to frame this starting point as some kind of virtual quantity that needs to be constructed on chain the moment we do the redemption. And this is what I want to talk about next. So the first thing I want to talk about is that this is well defined. And the mathematical proof is somewhat easy. So you can look at the three-dimensional graph where on one axis we have the redemption amount. On the other axis we have the, this is what we call the anchor reserve, the anchor collateralization ratio. And on the y-axis we have the collateralization ratio at any point in time. And then you can see that the value on this axis is strictly monotonic in the anchor value RA, which also means if we observe X and we observe R, which is something we do observe, then we can infer this anchor value RA, and this way we can reconstruct the whole curve, in theory. Of course, I haven't given you an algorithm to do this, and this is what I'm going to do now. So the algorithm has two steps. The first one is we notice that we can split up. This is the same graph. We can split up this graph into a number of discrete, what we call regions. And this is basically splitting it up by all of the case distinctions you saw a few slides earlier. And we can actually show that we can detect in which region we are without knowing the anchor point, so given only x and r. And this is like a little bit, requires a little bit of thought, but it's doable, and it can also be done pretty efficiently. And once we know that, the equation that computes RA from these two other variables is smooth. And it's only quadratic, and so once we plug everything together, we can solve a quadratic equation using a quadratic formula, and then we're done. And this is this theorem. So given the region x and r, we can efficiently compute the anchor point. And so overall, the algorithm for computing a redemption amount works as follows. First, we use this region detection algorithm based on the current state. Then we plug that into an algorithm that computes the anchor point from that. That gives us the whole curve. And then we do the integral over the curve to compute the redemption amount. And then when you kind of check what you actually have to do this, you notice that this only requires some arithmetic operations and at most 2 square roots. So it's also pretty efficient, and it's efficient enough that we can do it on chain. I wanted to highlight quickly one property, which is pretty nice about this. So the first property that we basically get for free is path independence. If we have several redemptions, one after the other, that's the same as having one big redemption. And this just follows from the fact that we integrate over a price to compute that. And the other one is that if you have like mint and redeem operations and you have some fee, then the protocol state only approves across such a path. And this is the way how to formalize that. So to conclude, today I have shown you a way to compare stablecoins by the redemption curve. I've shown you the idea of designing a redemption curve to design a primary algorithmic market maker. We've talked about this piecewise linear adaptive redemption curve, and I've talked about the implementation. So thanks a lot for your attention. Happy for questions, and you can find us here on the internet.
Thank you very much for the talk.